Hello, everybody. This is the lecture for Math 470 at Christopher Newport on finite fields. In the last video, I had said that we were pretty much done with fields, and apparently I lied. I decided that I was going to give you an overview of finite fields. We've seen one or two basic examples, but they're a very rich theory in particularly cryptography, coding theory, and other things involving computers, and so thought it would be a good idea to see a little bit more than just some basic examples. Okay, so story so far, we have seen some very classical fields. We've seen Q, R, and C, rational numbers, real numbers, complex numbers. The rational numbers are sort of the first complicated number system you see in grade school. The real numbers, these are what allow you to do calculus, basically. And then complex numbers, they kind of bridge in between both the algebraic and the analytic. If you've seen complex variables, you've seen they have a very rich calculus. They also have a very strong algebraic structure as well. All three of these fields are characteristic zero, and they are all infinite. Our work on field extensions in the Kronecker extension theorem showed that there are a whole mess of fields between Q and R and Q and C, depending on roots of polynomials. But classically, these are the main heavy hitters that you see. We've also seen that Z mod P will form a field when P is a prime number. If I'm dealing with Z mod N, where N is composite, it's not even going to be a domain, so don't even try. All right, but these have characteristic P, and all of them are finite. Now, these examples sort of lead to several questions. First, are there finite fields of characteristic zero? We'll see, no, there can't be. Are there infinite fields of characteristic P? And if we're looking at finite fields, okay, we've seen this one example. Are there ones besides Z mod P? Turns out there are. Okay, so let's look at the first two questions to begin with. All right, are there finite fields of characteristic zero? We already know the answer to this question. It really just can't happen. Recall, so characteristic, if it's characteristic zero, that means if I take one and I add it to itself, I never get zero. Well, if that's the case, then I can add one to itself arbitrarily many times. I will never get the same value back. And so it's going to generate inside my field a subring that's isomorphic to the integers. But any field that contains the integers has to contain its field of fractions, which are the rational numbers. But in particular, that means if it's characteristic zero, it contains an infinite set, hence it is infinite. All right, as for the second question, are there infinite fields of characteristic P? Yes, in fact, there are plenty of them. Some of them are a little more subtle in their constructions. If you go far in number theory, you see some really interesting things called the p-adic numbers. But a very easy and approachable example, take Z mod P, where P is a prime. I can take its polynomial ring. That gets me an integral domain. And again, every integral domain yields a field of fractions. So if I take that field of fractions, so-called rational functions over Z mod P, well, there are infinitely many polynomials, hence there are infinitely many rational functions, and that gets me an infinite field of characteristic P. All right, so that leaves the last question. Are there finite fields other than the simple Z mod Ps? Yeah, though there aren't very many in some respect. All right, so let's have a look at an example. All right, so let's take Z mod 2, and we're going to take the polynomial P of x is equal to x squared plus x plus 1 over this field. All right, well, to begin with, it's irreducible. It's a degree 2 polynomial, so in order to show that it's irreducible, I just need to show that it has no zeros. That's just a matter of evaluating it. So I evaluate it at 0, I evaluate it at 1, and I get 1 in both cases. In particular, I don't get 0, so it's irreducible. Okay. Then the Kronecker extension theorem tells me I can find a zero out there. We'll call it alpha. All right, when I take Z2 adjoined alpha, its basis is made, or a basis can be made, using the powers of alpha, starting with alpha to the 0 up to 1 less than the degree of the irreducible polynomial. All right, so the degree of the polynomial is 2, so I'm going to have from 1, I'm going to have alpha to the 0 and alpha to the 1 as my basis. Now, everything can be expressed in terms of the basis, so I take some multiple of 1, some multiple of alpha, and I add them together. There are 2 choices for the multiple, because Z2 has 2 objects, 0 and 1. So I can take both coefficients to be 0, and I get 0. I can take the coefficient of 1 to be 1, coefficient of alpha to be 0, I get 1. And then reverse them, I get alpha. And then if I take them both to be 1, I get 1 plus alpha. So that's it. This field has 4 elements right there. To work out their addition, well, we just have to keep in mind that we're working characteristic 2. So whenever I add a number to itself, I get 0. All right. So then it's just a matter of going through. 0 is the identity, so that's not going to change anything. 1 plus 0 will be 1. 1 plus 1, I'm adding a number to itself, I get 0. If I take 1 and I add it to alpha, well, I get 1 plus alpha. I get 1 added to alpha. And if I take 1 plus alpha, I technically get 2 plus alpha, but 2 is 0. So I'm left with alpha. All right. And then I run through it again. Alpha plus 0 will be alpha. Alpha plus 1, well, that's 1 plus alpha. Alpha plus alpha, that's 0. Any number added to itself, characteristic 2 is 0. And then alpha plus 1 plus alpha will get me again 1 plus 2 alpha, but 2 alpha is 0, so I'm left with 1. All right, and then if you run through for 1 plus alpha, using the same logic, you just get that row at the end of the table. Now, to work out the multiplication requires a little more finesse. We're going to use what we did with algebraic extensions in our algebraic elements. All right, so I take my minimal polynomial, evaluate it at my 0, alpha, and then I can express alpha squared in terms of the lower powers, namely 1 plus alpha. All right, and then it's just a matter, again, of going through that same process and figuring out what everything does. Well, multiplying by 1 doesn't change anything. So that's my first row. Now, if I take alpha times 1, well, that's straightforward enough. That's alpha. If I take alpha times alpha, I get alpha squared. But alpha squared is 1 plus alpha. So that takes care of those two. Then I've got to figure out what alpha times 1 plus alpha is. Well, let's do that. I take alpha times 1 plus alpha, I get alpha plus alpha squared. But alpha squared, using my irreducible polynomial, is alpha plus 1. This is 2 alpha. 2 alpha is 0, so I simply get 1. All right, now I need to run through the multiplication by 1 plus alpha. Again, it works similarly, and I encourage you, work it out, make certain you can get that last row, and when you do, you should get that. Okay, so I made a mistake, and so there might be a little bit of a chop there if I've managed to edit it out. So what we're going to do now is we're going to sort of blur the line a little bit. I know we were insisting that when we took alpha and squared it, we got 1 plus alpha, but I'm going to replace alpha by beta and 1 plus alpha, which would be the square, as beta squared in that multiplication table. So here's what I started with originally, and here's what I get with the substitution. Now, that right-hand table should be familiar to you. That is simply the multiplication table for a cyclic group of order 3 written multiplicatively. All right, so what happened, we've taken this field, it's got 4 elements, and when we looked at the multiplicative group, we got a cyclic group. It turns out that that's not a coincidence. All right, so before we get into a full discussion of finite fields, we need to take a little brief digression back to polynomials over a field for a moment. Okay, so in particular, we need 2 concepts. One is straightforward enough. We're going to say that an element alpha is a multiple 0 or a multiple root of a polynomial if you can factor multiple powers out of x minus alpha from the polynomial. Okay, so in other words, the zero has a multiplicity. It's not just a single zero there. All right, the other concept we need may look a little strange in an algebra class. We're going to define a derivative. We're going to take a polynomial in a field. We're going to define its so-called formal derivative to be the sum I equals 0 to n I times c sub I x to the I minus 1. In other words, it would be what you get when you apply the power rule from standard calculus. So, I just want to point out, this is a formal derivative. There is no limit involved. We are not deriving a power rule. We are simply saying the derivative of a polynomial is this beast. It is something that exists whether or not you can take a limit. I can't take limits in Z mod 2, for example. But I can still define this formal derivative. That being said, it's not overly surprising if you just crank out the formulas. You get the product and chain rules will hold for a formal derivative over a field just as they would for polynomials over the real numbers or such. Okay, so these two things are tied together by the following theorem. So a polynomial is going to have a multiple zero alpha if and only if alpha happens to also be a zero of the derivative. Okay, so to see this is just a matter of using our division algorithm and basically the product rule. All right, if it's a multiple zero, then I can express f of x as x minus alpha to some power k, where k is at least 2, times some g of x. All right, I take my derivative according to the product rule, and I've got a power of x minus alpha in both cases or in both terms, because k was assumed to be at least 2. So when I plug in alpha, I get 0. All right, now, if I know that f of alpha and f prime of alpha are both 0, well, I'll start the same way. I'll write f of x as x minus alpha times g of x because I know it's a 0, hence I can factor out x minus alpha. When I take my derivative, I get g of x plus x minus alpha times g prime of x. When I plug in alpha, I'm going to get 0 by assumption, but that means that g of alpha has to be 0. So g of x has a factor of x minus alpha, so I could factor that out back here, and I get that f of x has to be at least x minus alpha quantity squared times something. It is therefore a multiple 0. Okay, I will just apologize now. I don't know why this screen keeps popping up every time I pause the recording for a moment, but it does. Okay, so one more little bit of our digression. The following polynomial is going to be really important in a lot of ways. All right, so we're looking at a polynomial q of x, which is going to be x to the p to the n minus x. Here, p is a prime and n is a natural number. All right, so if I'm working in a field of characteristic p, if I look at the zeros of that polynomial, they're all going to be distinct. All right, so if I were to get a repeated root, so I'd have to have a repeated 0. That's the only way they couldn't all be distinct. All right, but if that's the case, then I would have to have a number alpha that was a 0 of both the original polynomial and its derivative. But the derivative of q prime is going to be p to the n times x to the pn minus 1 minus 1. But I'm in characteristic p. P is 0, so this first term completely drops out, and the derivatives is a constant. So I would need alpha to be a root of, or a 0 of this polynomial, and a root of a constant polynomial, but that's impossible. So I do not have repeated roots. So whatever the roots are, they have to be distinct. There can't be any sort of repetition. Okay, so now let's sort of delve into what we can find out about finite fields. All right, to begin with, we'll talk about their cardinality. So it turns out that the size of a finite field is very highly restricted. So we've seen Z mod P that has P elements. More generally, if I have a finite field, then its cardinality is P to the N. So some power of the prime P where P is its characteristic. All right, so the way to do this is to use some linear algebra. All right, so we go back to characteristic. If I take the subfield generated by 1 in a characteristic P characteristic P field, this is just simply Z mod P. All right, but that means Z mod P is a subfield of F. So F is an extension field for Z mod P. When I have an extension field, it's a vector space over the smaller field. Everything here is finite, hence this thing has to be even stronger, a finite dimensional vector space over Z mod P. So I take a basis. I will take, let's say F has dimension n. I take alpha 1 through alpha n. They are my basis vectors. So everything can be written in the form like so, where the C sub i's are unique, and I take them multiplied by the basis vectors, but those C sub i's, those coefficients, are each coming from Z mod P. So there are P choices for each of those coefficients. Hence, when I multiply them together, I get P to the N total elements. So I get that there are, P to the N, and moreover, P comes from the characteristic and N comes from the dimension of the space over Z mod P. Okay, so the multiplicative structure. All right, so if I take a field F, it has to have order P to the N. So now if I take an element alpha in here that's non-zero, if I take it to the P to the N minus 1, I'm going to always get 1. Okay, now this is just a matter of using a little bit of group theory. All right, so I know that F is a field. So I know that F remove 0 is going to be a group under multiplication. There's one less element, so it has order P to the N minus 1. Theorem of Lagrange says that if I have an element in a group, then the order of the element divides the order of the group. So if I take any alpha, its order must divide P to the N minus 1. P to the N minus 1 is a multiple of its order. So I take A, I raise it to its order, I raise it to further powers. I still get 1 every time. Moreover, I can strengthen that a little bit. If I have some alpha and I raise it to the P to the N, if alpha is not 0, take this equation, multiply through by alpha, I get alpha again. And if alpha is 0, well, 0 to any power is 0. So in particular, in a field of order P to the N, alpha to the P to the N is always alpha. All right, so continuing on, if we take this polynomial, x to the P minus x, inside a field of order P to the N, then it's going to factor, and moreover, it's going to factor into all linear terms. All right, so this is pretty straightforward. In the previous theorem, we showed that any alpha has the property that alpha to the P to the N is equal to alpha. In other words, it's going to be a 0 of this polynomial, and so x minus alpha divides it for any alpha. I can do that for any P to the N, any alpha of the P to the N elements of F. Those are all going to be relatively prime polynomials, and this has degree P to the N, so it has at most P to the N zeros. Well, I have found all of them. They are all different, and so I will get it to factor as x minus alpha 1, x minus alpha 2, all the way up to x minus alpha sub p to the n, where those are the distinct elements of F. Okay, we need a small lemma. We've seen a sort of a special case of this. We need a little bit more. All right, so if I've got a field of characteristic P, and I take a plus b and I raise it to the p to the n, then this is the same as a to the p to the n plus b to the p to the n. I can essentially ignore all the middle terms. All right, the proof is straightforward by induction. When n is 1, you've basically worked this out in your most recent assignment. So if I take a plus b, raise it to the p, I apply the binomial theorem, but these terms here, every one of them is divisible by p. I'm in a field of characteristic p, so all of those are 0, and so the only terms that remain are the first and the last, and so I'm left with a to the p plus b to the p. All right. I assume it true for n plus 1, it's just a matter of breaking it apart. So I take a plus b to the p to the n plus 1. This is a plus b raised to the p to the n to the p. So I can use my exponential laws, turn that into that. I apply my induction hypothesis on the p to the n power. And that gets me a plus b to the p. And then I'm back into my first case, which is a to the p plus b to the p. Okay, so now we're going to go slightly differently. So we've shown that every finite field has order p to the n. Now we're going to go the opposite direction. We're going to show that there is, for any prime p and power n, a field of order p to the n. Okay, so I start with z mod p, and I start with this polynomial inside that polynomial ring. All right, now this thing has p to the n zeros. We've only got p objects in here. We don't have enough. Okay, well, fine. We're going to take an algebraic closure. All right, so if I take an algebraic closure of z mod p, every polynomial factors completely in zp bar. Now, zp bar is too big. It's going to be actually an infinite field of characteristic p. So there's a second example of it, of such a thing. So we need to sort of pare it down significantly. So what we're going to do is simply pull out the zeros. We're going to pull out those zeros of the polynomial. So those things that would be zeros of this, or equivalently, they are equal to their p to the nth power. All right. Now, we showed that the zeros of that polynomial, once we have them, they are distinct. So this set K here has p to the n elements. Now it's just a matter of showing that it's a field. Okay, well, 0 and 1 are in K, that's not a problem. And then by our lemma, if I take alpha plus or minus beta raised to the p to the n, I'm going to get alpha plus or minus beta. And if I take AB, alpha beta, and raise it to the p to the n, I get alpha beta. So it is closed under multiplication. It's closed under particularly subtraction. It's non-empty. It's going to be a subring. But it's a finite subring because there's p to the n elements sitting inside a field. Every subring of a field is an integral domain, but a finite integral domain, as we've seen, is a field. So that gets me my field of order p to the n. There might be a bit of a jump in the editing, and I apologize. Okay, so two last results, neither of which I'm going to prove. The first is that if F is a finite field, then F star is a cyclic group. So once I remove 0, I will get something that's cyclic. This property is not tremendously difficult to prove, but it requires a knowledge of a theorem from the classification of finite groups that I don't believe any of you have seen in Math 370. So it would be pointless for me to try. Okay, the other thing is that if I have two fields E and F of equal cardinality, then they are isomorphic. Again, this isn't tremendously hard to show, but the main reason it's true is because both of them consist of the zeros of the same polynomial, namely x to the p to the n minus x. It requires a little more field theory than we have to really easily establish that isomorphism. We can do it without that, but it would get kind of messy. So I'm just going to state it. All right, so to summarize, what we've seen, given a fixed characteristic P, if I have a field of characteristic P, it has cardinality P to the n for some n. Conversely, for every n, I can find a field of that cardinality. All right, I know precisely the elements in there. They are precisely the zeros of this polynomial. If I have any two of those, they are isomorphic. And I know that the elements, the non-zero elements, form a cyclic group isomorphic to z mod p to the n minus 1. It has to be cyclic of degree 1 or size 1 less than p to the n. All right, that does indeed bring us to the end of fields. I promise I'm not lying this time. And next we're going to start talking about what are called algebras.